what would be the value of Z1 when the argument is infinity? Nobody knows? That would be another candidate of Thursday. Approach to zero, someone? Okay, so we'd rather look at the behavior of this function very well. Okay, when Ka sine theta is 0, meaning that, what does it mean? A is very small compared with wavelengths. Then physically it means we have to get the sound radiation as if we get the radiation from breathing sphere when K is very, very small, right? And certainly it does not strongly depend on sine theta because Ka itself is very small. For example, Ka is 0.001, and 0.001 multiplied by pi, and then 0.001 multiplied by pi over 2 doesn't really matter in the magnitude of this value. So when Ka is small, this function, or magnitude square of this function, if I draw in theta scale, does not depend on theta. But if Ka is very large, in other words, the vibrating piston's diameter is large compared with the wavelengths of interest. In other words, I am oscillating the piston with high frequency. Then this one look like this. In other words, it does depend very strongly on theta. This is the angle. In other words, when I'm vibrating cylinder, when I locate at the center, then I can hear. But if I move slightly over here, then I cannot hear because of the directivity pattern that is induced by this function. This is the directivity index. It's related with this index. In the medium range, for example, when Ka sine theta is somewhere between and this, that will look like this. Right? That is the result that we can get. What does it physically mean? Okay, for audio system, subwoofer, that means Ka is very small or large. Small, directivity is like this, omnidirectional. Therefore, we only need only one subwoofer if we just care about the directivity. But in the high frequency one, it has very high directivity compared with subwoofer. Okay. We need two, at least to feel the stereo sound. Or we need many if you want to experience so-called, I don't know what it is, 3D sound, but feeling that there are many sources, for example. Right? And Ka is, how to make a Ka large? For the selected frequency. We can increase the diameter. Okay? But if we decrease the diameter, right? For the selected frequency, we are reducing Ka. Then my question is, why tweeter size is small compared with the mid-range speaker? There are many things you can think about using this formula, and again, that is a very strong candidate to prepare Thursday examination. And Thursday examination, there are many OX problems, therefore. And you guys don't like it? Or do you want to have a question, for example, hey, try the sound pressure use Kirchhoff's integral equation? No? Okay. So, as I said in the beginning of this lecture, I said the objective of this course is to understand the fundamental. Therefore, we have to consistently focus on to achieve our objectives of this course. So I will not ask you to test your skill of driving integral equation and so on. And I assume that you guys are all very diligent to read the appendix very well. And some of them are already covered by giving you bad homework, which you already saw it, right? That is head-aching homework, but I said that this is graduate level course, so you have to do what exercise to handle the Kirchhoff-Helmholtz integral equation. Okay, now let's move on. We are not here to estimate the sound radiation from vibrating piston, right? That's too simple. We want to know the sound radiation from this plate, for example. Right? Right? And how can you do that? That can be done by applying what we learned. In other words, because everything we are studying is governed by and this is linear. Therefore, superimposing sound radiating from these three elements that we know can solve any sound radiation. Any radiation, for example, radiation from plate. For example, I have a plate that is vibrating like this.